Hello all, welcome to this channel cfdbaba. Today I am very excited since we are going to start our first tutorial using OpenFOAM. Today we are going to see turbulent flow-through pipe using OpenFOAM software. Today is the first tutorial of OpenFOAM. Many more tutorials are yet to come. Today, I will just show you the workflow of how to create a case in OpenFOAM from scratch and then run it on your laptop. You only need 3 softwares for running this case. First software is Salome, second is OpenFOAM, and third one is Paraview for post-processing. Today, we are going to create the geometry of this pipe in Salome and mesh it in Salome. Then we will import this file in OpenFOAM. Let's start by opening the Salome software. I am using Windows operating system for this tutorial. I have installed the Windows version for Salome. Let's click on New Document. Click on Geometry module. Here, select the interaction style switch. This option helps us to rotate the geometry using left mouse button, zoom in and out using the scroll button, and pan the geometry using the middle mouse button. We will create a cylinder as our pipe. To create the cylinder, click on Create Cylinder Shape. We need the cylinder to be oriented in the x-axis. Select the first option, select the base point as 0. Select the vector as OX. This will generate a cylinder in X direction. We want the dimensions of our cylinder as radius 0.1 and height 3. Note that all the dimensions in Salome are being used in meters. We are using SI unit for simulation of this pipe. Press apply and close. We have the pipe geometry ready. Now we need to create the boundaries where we will apply boundary conditions using OpenFOAM. Right click on cylinder 1 and click on Create Group. We need surfaces to define the boundaries in OpenFOAM. Click on the surface select filter. Rotate the geometry and click on the inlet face. Make sure that the flow is going in the positive X direction. Once you have selected the inlet face, click on Add. Name it as Inlet. Press Apply. You will see that inlet has been created. Select the walls of the pipe. Press on Add. Name them as walls. Press Apply. Rotate the geometry, select the outlet face. Click on Add. Name it as Outlet. Press Apply and close. Now we have all the 3 boundaries which we require to define boundary conditions in OpenFOAM. Now we will mesh this cylinder. Click on the Mesh module. Here, we can create the mesh by right-clicking on cylinder. Here, we can create the mesh by selecting cylinder and clicking on Create Mesh button. Here, we will use the algorithm as NetGen 2D. Here, we will use the algorithm as NetGen 1D, 2D, 3D. I am not focusing on creating a very beautiful mesh for this simulation. This simulation is just for demonstration purposes, and we will create a fairly good mesh which will solve our problem. Select the hypothesis. Click on Add Hypothesis and NetGen 3D parameters. Select the size for the cells as 0.02 for minimum as well as maximum size. This is in meters. Click on OK, click on Apply and close. Right click on Mesh, click on Compute. This will generate the mesh for your pipe. We are going to use tetrahedral mesh, that is the triangular mesh, to solve our problem. Click on the Fit All button. You will see the mesh on our pipe. We need to export this mesh to OpenFOAM. But first, we need to create the boundaries with mesh for our pipe. To create the inlet, walls and outlet boundary, select the mesh, right-click, and click on Create Groups from Geometry. Select Inlet, Walls and Outlet, and click on both the geometry arrow buttons for elements as well as nodes. We are saving the elements and nodes of our mesh. Click on Apply and Close. Now we are ready to export this mesh. Select the mesh, right-click, click on Export. Select the format as UNV file. We need a folder to save this mesh. I will create a new folder inside this location. Right-click, New, Folder. I will name it as 1_pipeflow. This is our new folder. Now we will save our mesh in this folder by browsing in the Salome tab. We are now inside this folder. I will name the file as mesh. Click on Save. Now we are ready to simulate our OpenFOAM case. Before that, we need the required structure of OpenFOAM to simulate this case. To get the structure folders, go in the Tutorials folder inside your OpenFOAM. My OpenFOAM has been saved in this location. Whenever you install OpenFOAM, you get a Tutorials folder along with it. Inside the Tutorials folder, go in Incompressible. We will use the Simple Foam Solver. Here we have the case for pipe cyclic. Right-click and copy this case. But we don't actually need this folder. Go inside and select all the folders contained inside this folder. Copy them and paste them in our new folder. Now we have all the folders required to simulate this case. Let me explain a little bit about the folder structure in OpenFOAM. In 0 folder, we have all the initial boundary conditions. In constant folder, we have the geometry and mesh. In system folder, we have all the files required to run the simulation. We have the solution and schemes files, we have the control dict, and we have the mesh generation files inside this folder. We will name this folder as 0. For OpenFOAM to recognize the 0 folder, it has to be named in this way. Now we are ready to import the mesh in OpenFOAM. Go in your Ubuntu terminal and enter the location of this folder. So we have to navigate to this folder through Ubuntu. In Windows, I have to type the location as cd for a change directory, /mnt to enter my computer, then F drive, then we go in this folder, then we enter the folder of OpenFOAM. So if I press capital O and if I press tab key, the console automatically enters the name of the folder. Now we need to go inside 1. So I will press 1 and I will press tab to enter that folder. Press enter. Now our location of the terminal is inside this folder. We are ready to import the mesh. The name of the mesh file is mesh.unv. We will use the command ideas unv to foam. Make sure that U, T and F are capital. We will give a space and enter the name of our mesh file, mesh.unv. Press enter. This will import the inlet, walls and outlet boundaries along with the mesh in OpenFOAM. To view this mesh, we can use the Paraview software. I have Paraview 5.52 installed. I am using OpenFOAM v1806. So let's open Paraview. So this is the Paraview software. We will open our file in Paraview. To open the file, we need a dummy Paraview file. We can create that by going in 0 folder, copy any file and paste it outside. Now we will rename this file to case.foam. I will open this file with Notepad++. I use this text editor to edit the text. I will delete all the content and I will save this file as an empty file. This is the dummy file which we will use to open the OpenFOAM case in Paraview. Go to Paraview and navigate to this file. We are now inside this folder. We will select case.foam and click on OK. Next, click on Apply. You will see the pipe that has been imported as a mesh in Paraview. But right now we can't see the mesh. To view the mesh, go in Surface and click on Surface with Edges. Now you will be able to visualize the tetrahedral mesh on our pipe. To view the mesh count, go in Information and here you can see the number of cells as 59K. You can even refine the mesh further in Salome. Once the mesh has been imported, we can run the simulation directly by using the SimpleFOAM command. Before that, let me explain to you what all files we have in these folders. The first important file is control-dict. This is located inside the system folder. Right-click and edit it with Notepad. You can see that we are running the SimpleFOAM solver. We will start the simulation from start time and the start time is at 0. Since we are running a steady state simulation, these time values are nothing but iteration values. That means the simulation will start from 0 iterations and end at 1000 iterations. We will set the maximum number of iterations to 100. We want the iteration to proceed with time step of 1. We want the simulation to write the solution after every 2 iterations. Save this file. The FV scheme and FV solution files contain the schemes and solutions used to solve this case. We will go through them in our upcoming tutorials. In the constant folder, we have our mesh folder that is named as polymesh. Inside polymesh, we have the boundaries of our files. If I open the boundary file with Notepad, you can see that we have our boundaries for the pipe here. You can even view the boundaries separately in Paraview. In the left corner, you can switch off internal mesh and turn on Inlet. Press Apply. You will see the Inlet patch on which we will define the boundary conditions. Turn on the walls, click on Apply. You will be able to see the walls of the pipe. Turn on Outlet, click on Apply. You will be able to see the outlet. To run this simulation, we just have to enter the command of SimpleFOAM. But before that, we need to know about all the files that are present in the folders. Next is the transport properties. The transport model is defined as Newtonian, and the value of kinematic viscosity is 1e-6. But this is kinematic viscosity of air. We need to simulate flow-through pipe for water. We will change the value of kinematic viscosity to that of water, which is 8.9 e-4. Save this file. Next, we will look at the turbulence properties. right-click and edit with Notepad. Here you can see that we are using the RAS realizable K-epsilon turbulence model to solve this case. The next folder is 0 folder. In 0 folder, we have all the files for defining the boundary conditions. We have the velocity, that is U, we have pressure P, we have nu T, that is turbulent viscosity, we have K, that is the kinetic energy, we have epsilon, that is the dissipation rate, and we have nu tilde. Let's look at these files one by one. Open the U file. Here, the internal field tells us in which direction the flow will go and with what magnitude. Currently, the flow is going in positive x direction with 1 meters per second. You can see the dimensions in this bracket. We don't need to include this function. The type for inlet is coded fixed value with a swirl, but we do not want any swirl in our simulation. I will delete this part. I will use the type as fixed value. I want a fixed value of 0.1 meters per second. So I will copy the uniform 100 and paste it instead of internal field. Here we can define the velocity as 0.1 in positive x direction. Internal field is the value with which our problem will initialize. I want the problem to initialize with 0 velocity in the entire domain. Then the velocity at inlet will be 0.1. At the outlet, we are using inlet-outlet boundary condition, which can allow backflow into the fluid domain if required. The boundary condition for walls is no slip boundary condition, but I would like to manually define the velocity on the walls. According to the theory of boundary layers, the velocity on walls is always 0. So I will define fixed value of 0. Save this file. Next we will look at the pressure file. Here we do not need this line. The pressure for inlet is 0 gradient. 0 gradient means that the software will calculate the values on this face from its adjacent cell zones. On the outlet we have fixed pressure of 0. On the walls, we again have the 0 gradient boundary condition. Save this file. Next, we will look at the K file. In the K file, we don't need this line again. We don't need this line in any of those files. We are using the turbulent intensity kinetic energy inlet, but I don't want to use this inlet type. I again want the value to be fixed value for inlet. I will remove the intensity and I want the value to be uniform 0.001. This is quite a small value and this is not the actual value. This is just a value used for initialization of our solution. The software will calculate the actual value as it runs the iterations. Save this file. The outlet is inlet outlet and the walls are KQR wall function. For any simulation, the boundary condition for walls in the K file will be this function. Next, let's look at epsilon. Open the epsilon file, remove this line. Again, we want the inlet to be a fixed value. So I will copy and paste the same boundary condition. I want the value to be 0.01. At the outlet, we can use the inlet-outlet boundary condition, and the walls will be epsilon wall function for any simulation in OpenFOAM in the epsilon file. Save this file. The last two files are nu T. Here, we don't need this line, and the value is always uniform 0 and calculated in the nu T file for all the boundaries. In the nu tilde file, We have uniform 0 and 0 gradient for all the boundary conditions. Save this file. Now we are ready to run this simulation in OpenFOAM. We have to enter the command SimpleFOAM. You can copy this command from the control dict. Right-click to paste SimpleFOAM in the terminal. Press enter. Here you can see that OpenFOAM has given us a very big error, but don't read any of these big lines. Always go to the root of the error and try to read what is the foam fatal error. It is that patch type for walls must be wall, current type is patch. So it is telling us that in the boundary conditions, in the polymesh folder, you can go in the boundary file. Here in the boundary file, you will see that the type for walls is patch. So we have two types of surfaces here. One is the patch and another is wall. So we will just change the type of walls boundary condition to wall. OpenFOAM will automatically assign the wall type boundary condition for walls and the patch type boundary condition for inlet and outlet. We can go back to our console and press the up arrow key. It will bring the command which we had used previously. Press enter. You will be able to see that now our simulation has started without any error, and it is calculating number of iterations in the console. We can view these results in Paraview. We will close the case we had opened previously. You can press delete to close the case. Go to File, click on Open. You will see that here the solution has been written for every 2 time steps. So I will just go to our folder 1 and I will open case.foam. You can see that new folders have been created. If you go to your original folder, you can see that time step folders for every 2 iterations have been saved in our folder. We will open case.foam to visualize the results. Click on Apply. Here you can see that the simple solution has converged in 67 iterations, and now we are ready to view the results. Here, at last, we see some colors after seeing the black screen. We have the pressure plot currently on the screen. It shows that the pressure at inlet is higher than the pressure at outlet, which is perfectly logical since pressure difference is required for flow to happen in the pipe. We can also visualize the velocity, but instead of visualizing the whole domain, we will create a slice in the YZ plane. Click on the Slice button. Select the Z normal and click on Apply. Hide Show Plane. You can rotate the geometry using left mouse button. Click on -Z Set View Direction. You can pan the geometry using middle mouse button. Let's visualize the results for U, that is the velocity. Here you can see the velocity inside the pipe, but this does not look uniform. But this is the velocity for first time step that was saved after 2 iterations. To view the velocity at last time step, we can go to the last frame and we can click on Rescale to Data Range. And now you will be able to visualize the final result of the flow through pipe in OpenFOAM. Here you can see that the formation of boundary layer is happening at the inlet length of the pipe. This is how we can simulate turbulent flow through pipe inside OpenFOAM. I hope you have found this video helpful. If you have liked this tutorial, make sure that you share it with all your friends and tell them to subscribe to this channel. Don't forget to like this video. We will meet again with new OpenFOAM tutorials in a new video. Goodbye till then.